Now this time we've got a radius of a spherical ball, and that's increasing at a rate of 0.8 centimeters per second. So that means the radius, dr dt, is increasing at 0.8. And we want to find the rate of increase in the volume. So we want to find dv dt at the point where the radius is 10. So there's our data that we've got from that. So how do we find dv dt? Well, we've got to use the chain rule because we've got nothing for the volume in terms of time. We do know the volume in terms of the radius because we know our formula is 4 on 3 pi r cubed, or dv dr would be 4 pi r squared. So we can use our chain rule for dv dr, and we've got dr dt, so we can put that together. So when an r is equal to 10, we can substitute the 10 in there and get 320 pi centimeters cubed per second. In question 6 here, we've got a volume of an ice cube is decreasing at 2.2 millimeters cubed per second. So dv dt will be minus 0.2. And we want the rate of the side of the ice cube that is decreasing. So we know that the volume with respect to time would be the dv ds over ds dt. Or we can manipulate that to also get ds dt would be ds dv on dv dt, because we know what dv dt is. So we can manipulate, because we know v is the side cubed, volume is the side cubed, so dv ds is 3 times the side cubed, side squared, or ds dv would be 1 on 3 lots of the side squared. So we can manipulate it that way. We can take the reciprocal of dv ds, which is ds dv, which we can then use. dv dt we know is minus 0.2, so we got ds dt in that form by using the chain rule, using what we had, the data that we had in our question to solve that. So when s is equal to 20, we do our substitution for the side being 20, and the times the minus 0.2 gives us minus 1 over 6,000 millimeters per second. Don't forget to add your units. This time the volume of the cube's increasing at 3 millimeters cubed per second. So dv dt is 3. We want the surface rate of increase in the surface area. So dA dt we could write as dA ds on ds dt, because we can get a relationship between the area and the side of the cube, but we need ds dt, which we haven't got at this point in time. What we can then manipulate, we know that dv dt is dv ds on ds dt, and the dv ds from the volume is 3 times the side squared. So we can manipulate this expression, this version of the chain rule, to give us an expression for ds dt in terms of s, because we can get dv dt is 3, which we know, dv ds is 3s squared, so ds dt would be 1 on s squared. So there's our expression for ds dt. We know that the ADS the area is 6 times the side squared, so the ADS would be 12s. And then we can start to put that together to get an expression for dA dt in terms of s, which is okay because we've got the side being 50. So it's not a problem getting an expression in terms of the side, because we can substitute that in. 12 on s, so where s is 50, we get 12 on 50, or 6 on 25. So just be wary of what type of manipulations you can do. It's all manipulating the chain rule to give us an expression that we can then do a substitution for the side to get us an answer for the area and its rate of change. This time we've got a parabolic shaped vessel. Is such that when it contains liquid at a depth of y centimeters, the volume of the liquid is 3/4 of y power 4. So the liquid's poured in the vessel at a rate of 40 centimeters cubed per minute. So, and what we want is the rate of the level liquid is rising at a depth of the liquid of 6 centimeters when the liquid is 6 centimeters. So what does that mean? Well, we've got a volume in this parabolic cup of 3/4 y to the power 4. So we could get and we want the rate of the level of the liquid is rising. So if we use that as y, we want to find dy dt. We do know the liquid is increasing at a rate of 40 centimeters cubed per minute as well. So dv dt is 40. So how do we manipulate it? We want dy dt. Now we know we can get v in terms of y, and we've got the dv in terms with dt. So could we get dy dv times dv dt? Because that's the 40. Dy dv, well, we know v is equal to 3/4 y to the power of 4. So dv dy would be 3y cubed when we derive this expression. And then dy dv, taking the reciprocals, would be 1 on 3y cubed. So that's where we are able to get our expression of 1 over 3y cubed there. And when y is equal to 6, we're able to do our substitution of y is equal to 6, and then get that value of 5 on 81 for the rate of increase of y with respect to time. So careful of how we manipulate it and what data we're given in the question. We've got a sphere expanding so that the surface area increases at a constant rate of 60 millimeters per second. So dA dt is equal to 60. We want the rate of the volume increasing. So what we want is dV dt. We can get dV dr and dr dt, but we don't know what our radius is increasing. So we have to do some manipulations first. We know dV dr would be 4 pi r squared. And we also can start to manipulate because we know dA dt is 60, which could be written as a chain rule of dA dr on dr dt. And again, we know what dA dr is because we know the area formula is 4 pi r squared. So dA dr is 8 pi r, which allows us to put that in. We know what dA dt is, which leaves us an unknown, really, as such, of dr dt, which is what we need. We need dr dt in this expression. So divide by 8 pi r on each side gives us 15 on 2 pi r, which we're able to do a substitution in for dr dt to get an expression for dv dt in terms of r, which is not a problem because we know that the radius is at a value of 20, which we're able to do a substitution of there. This time we've got a milk storage unit in the shape of an inverted cone. So when the gate opens at the bottom, milk pours out at a rate of equal to square root of h on t. What's that saying? Well, the volume is changing at a rate of square root of h on t. At what rate is the height changing? So we assume that the h there is involved with the height when h is 7.2. So what we want is the idea that the height is changing and we want to find the rate of change. So we want to find dh dt. That's our aim. What we do know is that we've got dv dt is equal to h. So the h dt would equal to h dv times dv dt, because we can get an expression in there. But what about dv to h? Well, the problem we start off with as well is that the volume for the cone is 1/3 pi r squared h, which is not all in terms of h. So we just can't derive v with respect to h to get something in this for this expression. What we need to do is a bit of a manipulation. We know it's 9 meters there, that's given to us. Our radius is 3.6 meters to start off with. Now, if we looked at any particular height at any particular point, we get a radius and a height, which would give us that expression. So the 9 on 3.6, or the 3.6 on 9 would equal r on h, or we could write the radius on 3.6, which would equal h on 9, which allows us to get r in terms of h, which means we can do a substitution and we can get our volume in terms of one variable h cubed. So there's our first manipulation. That's a bit of work there. So we've got to be really careful on how we're doing all that to start off with to get our expression there. And then d to h would equal the 12 on 75 because we multiplied by 3 pi h squared. So there, and dh dv, which is what we really want, is 75 on 12 pi h squared. So we know that dh dt is equal to dh dv on dv to t. We've got dv to t as root h on 10. dh dv we saw that was 75 on 12 pi h squared. And when h is equal to 7.2, we can do that substitution. We get 0.01. So what does that mean? It means the height is decreasing at a rate of 0.01 meters per second. So a little bit of manipulation. There's one where we didn't have our expression for the volume all in terms of the one variable. So we had to do the manipulation to get it all in terms of one variable. You can't derive there with the two variables. It's not allowed. So have a look through all those problems. That sort of goes through all the different types you can have, where we're manipulating using chain rule twice, using functions where it's all in terms of one variable, and being able to find the rate of change of time when there's no time actually given in expressions for volume, areas, or whatever else we've got to find.